we should and can start with the next talk by Sascha Trostorff from Kiel, and he will talk about exponential stability for post-Hamiltonian systems.
Okay, so thank you, Christian. Yeah, as the title said, I will talk about post-Hamiltonian systems, and in particular, I will present an hopefully new result on the exponential stability a bit. And this is a joint work on ongoing project, so there's still no archive article available at the moment with Rainer Picard, Bruce Watson from South Africa, and Markus Raurig. And yeah, so first I will talk a little bit about what a post-Hamiltonian system is in its easiest case. Then I will say a little bit about generation results of contraction semigroups. So can I associate a semigroup with this problem? And then the third part will be the result on exponential stability I'd like to present. So what we will consider at first are equations of the following form. So you see here you have the time derivative of an unknown u plus here is the spatial derivative, so everything is 1 plus 1 dimensional. So x is in a variable just in an interval a b, t is a time variable, so positive times, and u is assumed to be vector valued. And then you have here the time derivative of u. Here you have the spatial derivative not of u but of h times u. H here is an L infinity function, matrix valued. And then you multiply everything with P1, which is just a constant matrix. Here for simplicity, we take real matrices, symmetric and invertible. And the H is called the Hamiltonian, and this is assumed in the easiest case to be symmetric, almost everywhere, of course. And we call it's a matrix, yes, and it should be positive definite, so with a strict positive constancy. So this greater or equal sign here is meant in the sense of positive definiteness. Yes, so this is the setting. Of course, you need an initial value, which is given here. And yeah, now you ask yourself, well, can I solve this problem? So can I associate somehow not semigroup to this problem? So just throw the operator on the other side, and then you ask yourself, well, can I find suitable restrictions of this operator such that minus a generates a C0 semigroup? And what I will do, I will consider this on a suitable L2 space of the interval AB with reason Rn as my state space. And the second goal is, well, find a characterization for the exponential stability of the associated semigroup. Okay, so why is this class interesting, or what are typical examples? Well, this is very well suited for hyperbolic problems and also used very extensively in the framework of control theory. And the easiest example is about breaking strings. So here n is just 1, so we have scalar valued unknowns. And consider a string parameterized over an interval AB. And we denote by wt of x the vertical position of the string at time t and position x. Then all of you know that you can model this by the wave equation, here added with some constants or some material parameters. So you have the mass density here, rho, and you have here the so-called Young's modulus, which is something like the elasticity tensor in elasticity theory. And then it's more or less just a wave equation for W. And yes, you can rewrite this as a post-Hamiltonian system the following way. I wrote it here as a 2x2 system. And let us have a look at both equations. So if you multiply the whole equation with rho of x, then the rho of x, of course, occurs here in front of the second derivative. And if you read here the first line in this expression, you just get back the equation. That's very, very easy. You just have to look for it. And the second equation is just you have dt dx of w plus 1 over rho times rho. So this is just dt then you multiply it by dx. So this is dt dx w. There's a minus missing, I think. That's not so good. Somewhere a minus is missing. I'm sorry for that. So there should be a minus sign so that you have dx dt and dt dx, which then cancels out to 0. So I've just forgot a minus sign here. But nevertheless, this is more or less the setting. And then you get here the unknown u. You get here your matrix P1, you get here the Hamiltonian, and here you get the unknown u again. I'm not sure where the minus sign is got lost. I'm sorry for that. But okay, this is a typical example for it. If you stated correctly, I'm sorry for that. Okay. Now, how to prove now a generation result. In particular, I will just focus on contraction semigroups because everything is much easier there. There are also results for semigroups. I will comment on this later. There are well-known results of it. I can recommend the book of Birgit Jakob and Hans Zart, which was the lecture notes of an internet seminar on Hamiltonian systems. But I will provide here a different proof. And the idea is to consider this operator A, or to consider this operator, and apply congruence relations to it. So I just want to simplify this operator. And the first step is, this is classical, how to eliminate the h. So I want to get rid of this Hamiltonian, this L infinity function h. And what I do is I just consider the following operator, which I call x. This is just the usual L2 space on the interval, but I equip it with a different inner product. Namely, I put here the h inside. Recall that the h was symmetric and strictly positive definite, so this is a well-defined inner product, and also it's bounded, so the norm on x is equivalent to the usual L2 norm. So this is the new space, and if I now consider the operator u from x to this space L2, so the weighted space with the weighted inner product to the unweighted, and I just multiply every function with f. This is, of course, a bijective operator because you can just multiply with h of -1, which is invertible. And the adjoint is just the identity. That's funny. You can just compute this. And so you can write your operator P1 dxh just in this way. So you have a congruence relation now between this operator P1 dx and this operator P1 dxh, because u just is something like h, u star is something like the identity. But the difference is now that this operator here lives on the weighted space x, and this operator inside u star u lives on the usual L2. So you can deal with this one. And then since u is invertible and continuous, this operator generates a contraction semigroup even only if this operator generates a contraction semigroup. So you can focus on this operator on the unweighted space. Okay, so we continue with this operator here. And the next step is we want to get rid of the P1. And well, I recall P1 was just a matrix, a constant matrix, n times n, which is symmetric and invertible. Okay, what to do? Yeah, here's the recall. Well, I just diagonalize it with a unitary matrix. So I can write this as a congruence relation to a diagonal matrix with the eigenvalues on the diagonal. And since P1 is invertible, every eigenvalue is non-zero. And then I can just define the following diagonal matrix Q, which is just yeah, again, something has happened which shouldn't happen. So there is a sign missing at one place. Yeah. So yeah. Okay. Now, first, you can just write this, and then you have here still a diagonal matrix. I'm sorry, I've just forgotten to write it here. Another diagonal matrix with 1 and -1 in the diagonal. So you get here now the matrix D1. Oh, I can write it here. So this is D tilde inside it. And then you can, so I have here still the D tilde. And the D tilde, as I told you, is something like you have some 1s on the diagonal and some -1s on the diagonal. And then you can apply another congruence, and I didn't write it down, I'm sorry for that. Then you just swip your, you just, how to call it, reflect your function on the symmetric interval. So at the middle point between A and B, to get rid of the minus signs here. So you just swip, and because of the derivative, you will get an additional minus sign here. And putting everything together, you end up with the following. You find an invertible mapping W from your weighted space to your unweighted space, such that your operator P1 is congruent to just the derivative. So if you want to have a contraction semigroup, a generator of a contraction semigroup, you have to consider generators of contraction semigroup dx, and you can translate everything back. So that's the next result. We just look at the operator dx, just a partial derivative, on the unweighted space, and ask ourselves, well, when is this operator emigrative, which means that minus d generates a contraction semigroup. And this is not so hard to compute. You can just characterize this in the following way. It's more or less the same as Rainer has presented, and indeed this was the initial point to start the research Rainer has presented to you. This is equivalent to the following effect. You find a matrix M, which is less or equal than 1 in the operator norm, such that you can write the domain D the following way. You take H1 functions, so that you are a restriction of dx, of course, you need to differentiate. And the boundary condition is given in that way. So you link the left endpoint with the right endpoint via in this matrix M. And this is equivalent. So this is not very hard to do if you have the dx, and if you now translate everything back, so you go from this operator back to this operator by applying this V and V inverse, you get the result which was proved by Birgit Jakob, Kirsten Morris, and Hans Zwart in 2015, namely that you can consider or can ask yourself, when you have an emigrative operator A, which is now a restriction of this operator on the weighted space. And if you do everything, you end up with another characterization, namely you consider every function, so you get a domain again, you can get every function in L2 in this domain, such that HU is differentiable, so that you can apply this thing here. If HU is differentiable, Sobolev embedding tells you that you can evaluate at the endpoints A and B, and then you find a matrix B, which determines your boundary condition, and the B has to satisfy such a condition. It's rather more difficult than the other thing, but if you just do the computation backwards, you end up exactly with this condition here for the B. Yeah, that's indeed the proof. So you have this congruence relation here. Then you know how to construct emigrative realizations of dx. So A is emigrative if and only if this operator is emigrative. Then you know when this operator is emigrative by the previous theorem, and then you have to translate everything back and end up with this expression here. I want to skip the technical details. Okay, so this is a well-known result. Also in this paper of Birgit, Kirsten, and Hans, you can find criteria for the generation of a C0 semigroup, so not a contraction semigroup, so no emigrativity, but then you need more regularity assumptions on your H and your P1. Yeah, okay, but I don't want to go into detail here. Okay, so far so good. Now we come to exponential stability. And throughout, we assume now the following. So assume we have an emigrative realization of our operator on our space X. That means the domain of A can be written in that way. Yeah, you have such a matrix B. And yeah, there's a result from Jochen Schmid in 2018, which states the following. So you want to know when minus A, which is now a generator of a contraction semigroup, when is the semigroup, the associated semigroup, exponentially stable? And there's the following result. if you have this property here, so you find a kappa, a positive kappa, such that for every element in the domain of A, you have this estimate. So you have here the inner product in X in the weighted space of U and AU. And this is greater or equal than kappa times the Euclidean norm of HU evaluated of one of the endpoints. So A or B, doesn't matter. Then you can find out that minus A generates an exponentially stable convection semigroup. And Jochen Schmid uses the assumption that H is a bounded variation. So you need more regularity for H to get this result. A remark, you find a previous result in the same manner. So this assumption here was also used in the article by Villegas, Zwartlik, Orek, and Maschke in 2009, where they assumed that H is more or less Lipschitz continuous. So stronger assumption of bounded variation. Okay, so my aim is now to remove this assumption and just to get the same result without any additional regularity for H. So that this should also hold for L infinity H. Okay, and the idea to do is more or less the same. We will use the Giat-Pruss theorem at first to get exponentially stable stability. What was the Giat-Pruss theorem? All of you may know it. So minus A generates an exponentially stable C0 semigroup on a Hilbert space. So that's a pure Hilbert space theory here, even only if the resolvent is uniformly bounded on the right half plane. And well, since I know that minus A generates a contraction semigroup, I know that the resolvent exists for all Z, positive Z. And away from the imaginary axis, I know that this is uniformly bounded. So you can rephrase this for this case, just to say that the imaginary axis should belong to the resolvent set of minus A, and along the resolvent set, along the imaginary axis, the resolvent should be uniformly bounded. So that's the same if you have a generator of a contraction semigroup. Okay. So we want to use this, and we do the same thing as before. We use congruence relations, but with one difference. So recall what I did. I had eliminated the H by introducing this weighted inner product, and then I have diagonalized the P1. And this time I don't change the sign of the eigenvalues. So I keep with this matrix D tilde I wrote down before, where you have some ones and some minus ones. So you don't change the sign of your eigenvalues. So this is now the congruence relation. And so you have, so to say, K eigenvalues with positive sign and N minus K eigenvalues with a negative sign. And then you just normalize them to be 1 or minus 1. And then I decompose my space in RK and N minus K, so corresponding to the numbers of the positive and negative eigenvalues. And every time I will write X hat for the first K components of a vector, and X check for the first K coordinates, and X hat for the last N minus K coordinates. And well, then I can do more or less the same thing I just write everything down. I still want to control these this resolvent using the Giat-Pruss theorem. And I can do more or less the same computation as before. I just apply certain congruence relations to eliminate the H and to eliminate everything else to get the P1 in this form. And then I end up with a resolvent of that form. Yeah, so I get the Q here. This comes from the congruence relations. The Q turns out to be an affinity function, which is positive definite and symmetric. So a matrix value function has an N missing, sorry. And then you have here the matrix D, which is this one now, yeah, this inner matrix. So this is the D. And then you have the C here, which is again
Sascha, there is no sound.
Yeah, I think your audio is lost, Sascha.
Sascha?
Probably not only audio, but also the connection.
Everything stopped.
Probably.
We had such a problem already in the morning at another section. We have lost already one speaker just in the middle of the talk.
So I would suggest to just wait a bit. Maybe he's back in a couple of seconds.
Yes. But Christian, probably you can contact him by
Yes.
his.
Let me do so.
Yeah.
Hello.
Hi. Welcome back.
By the way, when I left the meeting?
At about slide 42.
I'm sorry for that. I didn't recognize it.
Never mind.
Yeah. Now I understand why Rainer has to try to contact me.
Yes.
Okay.
Somewhere over there, yeah.
Okay. Let's hope the best. So the only thing I want to say is, so you do some congruence here, and you want to control this resolvent by the Geert-Pruss theorem, and instead of that, you can control this resolvent. And that's the next aim. So what do you want to have is that this resolvent is uniformly bounded if you plug in element Z in the right half plane. And this you can do because C is just a restriction of the derivatives. So the resolvent is just the solution of an ordinary differential equation, and you can compute it by hand. It's a little bit complicated because you have these strange boundary conditions, but it's manageable. At least if I could do it, you can do it also. Yeah, and then you get a terrible expression. Namely, you have to consider these terrible metrics here, but it's just a matrix, yeah? N times n matrix. So what are the ingredients? The D is this matrix with the 1 and the -1s, yeah, corresponding to the positive and the negative eigenvalues. You have the integral of the Q. So Q is this matrix where you function here. And then you take the projection onto the last n minus k coordinates of this exponential. Then you add the projection on the first k coordinates. Then you multiply everything with your matrix M, which is inside the boundary condition. And then you do it vice versa, where you now just take the projection onto the first k coordinates of this matrix, and you add the projection onto the last n minus k. And this whole matrix, which now depends on T, should be invertible and uniformly bounded. Okay, this is the theorem and the characterization. And well, I guess you can never compute this really, so it's more of a theoretical interest. But what you can show, at first, the first question, or I asked myself as well, if this matrix is invertible, maybe we get this for free, so we don't have to assume it. But no, this is just wrong. You can construct matrices ST, which are invertible for each t, but the supremum is infinite, so you have to assume it. We have constructed a concrete counterexample. Okay, so well, now I can everything do for this transformed resolvent, and then I can again transform everything back, and I get this result. So it's more or less the same. So the minus A generates an exponentially stable contraction semigroup, even only if now this matrix is, this is the B again from the boundary condition. This is the Hamiltonian H, and this is the matrix B1. You get this strange expression here. This matrix should be invertible for each t, and the inverse should be uniformly bounded. As I told you, this matrix is not nice computable, but what if you have this characterization here, you can actually prove the theorem I promised you, namely that you get the complete analogous result here without any regularity assumptions on the H. So without any regularity assumptions, if you have this estimate here, the same as Jochen had in his paper, without any regularity of H, you get that minus A generates an exponentially stable contraction semigroup. Okay, I'm sorry for the interruption, and thanks for your attention.
Yeah. Thank you, Sascha, for this interesting talk. Are there any questions, comments?
I have a comment.
Okay. Yeah.
One might wonder for a moment that the characterization works with the application of previous results, but this is not the case. This is really, you really solve the ordinary differential equation Sascha mentioned, and then you show this uniform bound on the imaginary axis. So it's really a genuinely new proof and not a new way of looking at this exponential stability bit. And since apparently there was an open problem session or an open problem book around this conference, there's also an open problem here, because we just saw that Porter-Hamiltonian systems are congruent to the transport equation, if you will. And one might wonder whether the exponential stability is preserved under congruence. And this is funny, because if you take an emigrative operator, congruence preserves emigrativity, hence it preserves the generation of semigroups for minus the operator. So you might wonder whether exponential stability is preserved under this congruence too, but we don't have any idea whether this is true, and we just used or we figured out the way of showing exponential stability by means of this congruence somehow, but not actually using the full power of the congruence. So it's kind of funny that it's somewhat twisted, and we were looking for a more general perspective, but we didn't find any.
Okay, thank you. Are there further questions, comments?
Maybe I have a comment in this direction, or to what Markus just said. I think if this would be true, then exponential stability would be independent on the function h. Is that true? And there's a nice counterexample, which you either find in the PhD thesis of Björn Augner, but it goes back to a paper of Engel, where it actually shows that the exponential stability depends on this function h. So this would get lost. It's not like with contraction semigroups. Contraction semigroups, it's quite nice. You go to this weighted you have this weight in the L2 space, and you can somehow, what also Sascha just did, through the H away in some sense, and you still just look for contraction semigroups. But with exponential stability, the stability really depends on this function H.
Yeah, this is very, very good comment. Thank you very much. I didn't know of this example. Did you, Sascha?
Just look up in the PhD thesis of
Yeah.
Augner in section chapter 4.4, and I think it actually goes back. There's a paper by Klaus Engel, I think 2013 or something like that.
Okay.
Thank you. I mean, looking at the characterization, I mean, one sees that it does depend on H, but one could argue, well, it just depends on the integral average of H inverse, right? I mean, this is the characterization. So if you had different H's, they must have different integral averages of the inverse. So this is really what is one upshot, if you will, of the characterization just presented.
Also true.
Okay, further comments?
I have one small question, and maybe Sascha can share the slides again.
Yeah, I'm sorry. Yeah.
I don't remember the number, but it was at the beginning where you show the equivalence of, what was it, of the generation for contraction semigroup.
Yeah.
And you had some boundary conditions in your formulations. Yeah, and I'm wondering, I mean, it's also true if you set M to 0, then you have the boundary condition U of A 0, but you can do more or less the same with U of A. You can also have U of B is 0, but your condition doesn't reflect that.
No, then you transport in the wrong direction. So you get a, I have always the problem with left and right, so I don't know which direction, but no, you can just allow one thing to be vanished. And this should be now, if this theorem is correct, let's hope the best, then U of A equals 0 is okay, but the other way around not, because you should just shift in the wrong direction.
This is only the transport equation.
Yes,
okay,
yes,
I get
yes.
it. Okay, yeah, okay. Then sorry, then everything is fine.
Okay, are there further questions? I don't see any further. Then let's thank Sascha again, and also thank all the speakers of this afternoon session.